that after 6 to 9 months of weightlessness, you would lose so much mineral from bone that you would end up with seriously fragile and permanently fragile bones.
Into orbit, your face gets puffy and your voice gets nasal and you feel kind of funny, and you feel that way as long as you're up here. You just get used to it.
And with a puffy face, you can't read the facial gesture. So all of a sudden, somebody comes along and they make a funny remark, and you don't know whether it's a snide remark or it's a funny remark, because you get that clue from the way you read the face.
You won't have living in space, real living in space, until human beings are allowed to function as father, mother, brother, sister, and all the different roles that we live out on Earth.
For millions of years, the human body has evolved here on Earth. This planet is our life support system. It provides the air we breathe, atmospheric pressure, protection against radiation, livable temperatures, and the force of gravity. When we encounter conditions beyond the body's tolerance, we use technology to provide the essentials of survival. This incubator, for example, is an artificial life support system that gives a premature baby a fighting chance at life. On my flight, the shuttle served much the same function. An aluminum shell and a few panes of glass. A fragile cocoon that stood between me and the hostile environment of space. In this episode, we'll look at staying alive in space. We'll examine the technologies of survival that allow us to function beyond the Earth's atmosphere. At first, for a few hours and days, then for months and years, and ultimately, perhaps, for a lifetime.
Houston Discovery, we got a tally-ho, and it's dead center in the coas.
Roger that, sounds good.
Space is the most unforgiving environment yet encountered. It could hardly be more different than Earth, containing extremes of heat and cold, a near vacuum, increased levels of radiation, and zero gravity. The human body cannot survive these conditions, so we take the necessities of life with us. A space vehicle must be, first and foremost, a life support system. A spacesuit provides the bare essentials, allowing astronauts to work for a few hours in uniquely hostile conditions. Small and flexible, its protection wraps around the body like a cocoon.
You have to be inside your own little spaceship in order to survive in outer space in a vacuum. And that's, of course, what a spacesuit is. It's a human-shaped spaceship. And it has fans and motors and pumps to provide you cooling water and oxygen and suck away all the exhaled air that your body has already used and purify that for use again. And that whole ensemble of equipment that you're ensconced in weighs on the order of 230 to 250 pounds.
This is our current shuttle spacesuit, composed mostly of fabric elements as you see on the table here. The innermost layer is a urethane-coated nylon. This is the pressure gas barrier, faced up by a Dacron polyester restraint layer, an abrasion layer with a neoprene coating. Then we have a series of thermal insulation layups, aluminized mylar. And the outermost surface of the suit is a material that we call orthofabric. It provides abrasion and snag-proof protection. Well, prior to having a crewman or a test subject get in a spacesuit, we outfit them with what we call our liquid cooling garment. I've got Troy Stewart here, who's going to be our subject for our 8 PSI suit demonstration, wearing the liquid cooling garment. And what it really is composed of is a series of small tubes that cross over the body surface. There's a small liner in here between the crew member or the subject and the tubes to give them a little comfort. These tubes cross over the main torso, around the back, down the legs, and down in the arm area. They're reconnected through this manifold, and the water is circulated from our backpack, or our life support system. And it's a primary method of removing the metabolic heat from the crewmen inside the suit.
This complex piece of plumbing is the control center of the spacesuit.
The functioning of this backpack is critical to an astronaut's well-being during a spacewalk. The longer we stay in space, the more demanding life support becomes. A spacecraft offers more than basic protection from the harsh space environment. It offers relatively comfortable Earth-like conditions, what the astronauts call a shirt-sleeve environment. The vehicle is a rudimentary home, providing the necessities for a stay of days or weeks at a time. Food and water, room for work and recreation, sleeping accommodations, toilet facilities, and much more. A serious failure of the spacecraft's life support system means death for the crew. In 1971, 3 Russian cosmonauts died when their Soyuz spacecraft lost internal pressure during its return to Earth. This plane, called the KC-135, is flying a series of roller coaster climbs and dives. Each time it goes over the top, the passengers experience about half a minute of zero gravity. Before spaceflight, the human body had never encountered zero G for a sustained period. We've been in space for only 1 generation, and we're still trying to understand the effect of this condition. Flying a plane like the KC-135 is one of the few ways we can recreate zero G on Earth, and only for seconds at a time. But even these brief snatches help us to understand its physiological impact. Motion sickness, for example.
We have tried applying motion sickness tests to people on Earth and then recording their susceptibility to various motions on Earth to see if from that we can predict who's going to get sick in space. And so far we have not been able to do so. There have not been good correlations, unfortunately.
There
we go, guys.
You're walking good.
Are you ready to start, Ken?
Ready? Okay, here we go. Okay. 1,000. 1,000, 998, 996, 996.
This machine, called the Peripheral Angular Mover, or PAM, was invented by Ken Money, a physiologist and member of the Canadian Astronaut Group. It's used to test people on Earth for susceptibility to motion sickness. Motion sickness is the first and most obvious effect of zero gravity. It has affected nearly half of those who have flown in space. Space scientists hope one day to develop Earth-based tests to predict who will get sick in space.
Well, helps if you're a little masochistic, but anyway. Slight nausea is the standard criterion you reach before stopping, and so when you experience slight nausea, you yell, "Uncle," and Bob Chung lets you out of the fiendish machine, which is making you sick. And you have thereby, by measuring the time it takes you to reach this standard level of sickness, you have a measure of your susceptibility, which does vary from day to day, but it varies even more from individual to individual, just as, in fact, space sickness does. Space sickness and seasickness and car sickness are all the same thing. It's all motion sickness. Camel sickness is the same thing. Lawrence of Arabia got sick on camels. Whenever the motion causes the ear to send false information to the brain, and it does it by exceeding the normal dynamic range that the organ of balance in the ear can report. When that range is exceeded by a motion and the ear reports false information to the brain will think that it has been poisoned and it will cause vomiting. And this illustrates the central role of the organ of balance of the inner ear in all these forms of motion sickness. And in fact, people who do not have an inner ear are utterly, 100%, absolutely immune to motion sickness of all kinds.
The longer we stay in space, the greater the impact of zero gravity on our bodies. Zero G looks like a lot of fun, and it is, but it soon begins to affect the heart, the blood, the immune system, the central nervous system, the bones, the muscles. Muscle wasting occurs quickly. A lot of exercise is needed to stay in shape. Fluids shift to the upper part of the body, producing what the astronauts call puffy face. This has serious effects. It causes the heart to become smaller and to beat faster, and results in a drop in the volume of blood. The physiological changes that occur in space are signs of adaptation to zero gravity. But this means that when the body returns to Earth, it is less well equipped to deal with normal gravity, and this can cause trouble. All in all, coming back to Earth, even after only a week in space, is a rude shock. The balancing system in the inner ear has been affected by zero G. Muscles are weak, and walking can be difficult. Blood rushing to the feet can cause lightheadedness. This is one reason why astronauts and cosmonauts who have been on long flights are made to sit or lie down as soon as they return to Earth. Our bodies are the product of a one-gravity environment. Zero gravity has many subtle physiological effects. Loss of calcium from the bones is one. Bones lose calcium in zero G because they're not bearing weight as they do on Earth. Astronauts who stay in space for months or years could end up with fragile, easily fractured bones, and they face an increased risk of kidney stones.
With bone demineralization, once a crewman gets exposed to zero G, they start to lose calcium in the bone. And there's an increased calcium that goes from the bone into the blood. The kidneys filter the blood. There's an increased calcium level in the urine. And that is when you're predisposed to the onset of renal stones.
The longer we stay in space, the worse the bone calcium problem will become, unless we can find a way to prevent it. Scientists are looking for solutions, trying drugs, diet, calcium supplements, or strenuous exercise may be the key, making the weight-bearing bones work as hard in space as they do on Earth. If that fails, only one option remains: artificial gravity.
If space station people or Mars travelers or so on exercise on a daily basis with the right kinds of forces simulated, that might stop the loss of calcium or make it very, very small. That would be fine. The other way around it, if that doesn't work and if we can't find drugs or hormones or things like that will stop the loss of calcium, is simply to rotate the spacecraft when you go on long spacefaring voyages. Create artificial gravity like the space station in the movie 2001, which was a great big rotating donut.
We'd like to avoid building a rotating space station, but our bodies may not let us.
The problem is, can we move in one generation or two generations where we fully adapt to zero G, having evolved in a gravitational environment? And I'm guessing now, but my guess is that we probably won't be able to do that. There's no air in space, so we take our own air. There's no food, so we take our own food. There's no water, we bring our own water. There's also no gravity up there, and I think eventually we'll have to bring our own gravity, especially when we get to a mission that demands long-term habitation or procreation or something along that line.
Solar flares are huge storms on the sun that send out waves of radiation, another threatening feature of the space environment. The longer we stay, the greater the accumulated biological damage. And when we head for the moon or other planets, we're even more vulnerable.
If you then are going to Mars, you're outside the Earth's magnetic field. Your normal daily dose of radiation is quite low, but you are subject to that chance of a big solar flare with particles washing past the spacecraft, giving you a very high dose, perhaps hundreds of rads, enough to kill you. So what you need on a spacecraft like that is a radiation shelter, some small, thick-walled device into which you can crawl and stay there for 24 hours or so until the peak of that flare is passed. Now, there's one more kind of radiation, which is cosmic particles. These are very high speed, very heavy in some cases, fragments of atoms, including iron and some even heavier atoms, which are coming not from the sun, but from outside the solar system, from somewhere in the universe. And what happens is that if you put up a shield around you that would be great for solar flares, it'll stop some of these cosmic rays, but they're going so fast that they divide into secondary radiations, which are more damaging than the primary one is, which gives rise to the paradox that if you're going to Mars and you've got this radiation storm shelter to use for solar flares, you must get in it for solar flares, and you'd better stay out of it at all other times because the radiation dose is higher inside that storm shelter from cosmic rays than it is behind a thin-walled ordinary spacecraft.
Staying alive in space is expensive. We can't afford to lift tons of oxygen and water off the Earth. If we want to build a permanent home in space, we'll have to look for new, more efficient ways to supply the essentials of life. Recycling is the key.
We talk typically about a 90-day resupply mission, so we're talking on the order of 1,800 pounds of oxygen alone that would have to be brought up if we did not close the oxygen system. In the case of the water system, if we provided the services we currently plan to provide, since it's approximately 50 pounds per man day needed or 400 pounds per day for an 8-man crew, then that means you'd be supplying approximately 40,000 pounds of water with this resupply vehicle, which of course is not a very feasible thing to do.
We'll even have to reclaim clean water from urine. Every recycling option must be considered.
The drinking of urine by the crewmen may be the biggest challenge we have as engineers. It's probably more a non-engineering challenge because it's a psychological thing. You've got to get the crewmen convinced that they will drink urine and indeed drink somebody else's urine. That's probably the biggest problem.
As we stay for longer periods in space, we'll need even more life support systems, including medical services. In the future, we can expect medical emergencies and industrial accidents. By putting a mini hospital in space, we can save lives that might otherwise be lost.
The prime limitation in terms of doing something like general surgery in zero-G is having the in-flight expertise on board to actually do the general surgery. Equipment is not near as much of a driver. We think we can get adequate equipment on board such that we could do general surgery, or we could do something like an appendectomy if we had the expertise, that is a surgeon on board that was qualified to do those kinds of procedures.
The Soviets have had the longest missions and have already experienced a medical emergency in space. One mission was aborted months early when a crew member became seriously ill.
They were supposed to be there for 6 or 7 months, but halfway through their planned mission, one of the crew members, the commander, Vasutin, began to show signs of irritability, lack of sleep. He was becoming, and in fact, fever. He had suffered some sort of infection, and not to this day have we really learned the full nature of this sickness. But it got to the point where over several weeks in space, he was suffering painful inflammation somewhere in his body. They won't quite say where. But it got to the point where it was getting worse, and they felt his life was in danger. The treatment in space was not working properly, and so it was decided to bring the mission home. There was no way to take him home by himself. There was only one ship, one Soyuz T, hooked up to it, so the whole crew came back. But Vasutin was so ill that his flight engineer was put in command of the mission and, in fact, sat in the pilot seat on the Soyuz during the landing.
Loneliness, fear, anger, boredom. We take the entire range of human emotions with us. If we are to live in space, we must come to terms with the human aspects of the experience.
The The Soviets have, from the very beginning, thought that the psychological aspects of long-duration space flight were one of the maybe tall poles in the tent. And from the very beginning, they started out with a group that they call the Group for Psychological Support. And they were a little naive in the beginning. The first thing they did for one of their long-duration flights was take 3 guys, put them in a car, and tell them to drive across Siberia, because they figured that was really one good way to find out whether 3 guys could live in isolation and confinement. If you've driven across the country in a car with your family in the summer, you probably understand that was a very good test. Now they're getting much more sophisticated. They use voice stress analysis. They use compatibility testing. They have a sophisticated training program. They're not as far as they'd like to be.
The Soviets, while they may not discuss the hardware involved in their flights, are very open about their psychological feelings, what they feel, what they experience, what they think. This is almost a traditional Russian character to talk about their feelings very openly, and they do that in their space diaries.
Discipline is very strict. You cannot weaken. Just fail one command and all the work done by you and by others could be for nothing. But in space, both your work and your conscience are on view for all, and you cannot hide behind others.
From the Russian experience, it seems that about 28 to 30 days into that experience, there's a window that you go through, and the energy that it takes to deal with the isolation and the confinement and the stress and the novelty of the environment just gets so high that you can no longer deal with a lot of these small things. So the small, tiny things that are irritating and disturbing and bothersome begin to increase the level of stress. It's the theory of the straws in the camel's back. And you can deal with a lot of straws for a short amount of time because you have these spurts of energy. But in space, there's no place you can go and sort of yell. There's no place you can go and blow off steam.
There are tense moments between the crew, but no outburst can be permitted. Otherwise, if a crack appears, it will get wider.
Ryuman, who's one of the very experienced cosmonauts, reflected on his way to launch on the O. Henry story, where 2 men were locked in a room for 2 months and wound up murdering each other, and wondered what essentially spaceflight was going to consist of for him. And so what they did later on is they tried to find out if there were certain human traits that went well together in space.
Several more days passed, and we sensed the atmosphere was becoming charged. Sometimes we differed in assessing the same event. I soon noticed that Georgie became even less self-controlled.
If you put 2 detailed people together and all they do is nitpick, they're going to drive each other nuts after 6 months, you know? Or if you have 2 people who always look at the big picture and never pay attention to little details, they could die because they might overlook something that's a detail, but it's very important.
Every word had a meaning. Even the tone was important. It was important to really be sensitive to your friend, to know, to understand his mental state, and to analyze the possible consequences.
And what we want to do is now build a place in space where a large number of very different people can live and work comfortably and synergistically, so that when they go up there, they're not going to be so tired and so stressed and so disturbed and so irritated by their environment and the discomforts and the inadequacies that they don't do a good job, because it costs a lot of money to send that guy up there.
Each evening, I kiss the photograph of my son. He looks out at me so kindly that when things are difficult, I say to him, "It's nothing, son. I'll manage. Papa will not let you down." Lyusha and little Vitaly had written me many letters. I lay down in the sleeping area, but I could not close my eyes for thinking about the letters and what we will say when we meet.
Right now, when you go into space, you have one role, and that is your job. And you have to leave so much of your life on Earth, your friendships, your fundamental relationships with your husband and children, whatever. And those relationships have to somehow be transported into space someday for people to truly live there for long periods of time.
Is there room for strong feelings and emotions in a spacecraft? They can get in the way of work, compromise the mission, possibly even endanger the crew. But whether or not they belong in space, our emotions are a part of us. We are only human, after all, and we take the totality of our human nature with us.
Space stations are the next logical step. But before we can build them, we need to develop new tools and materials and to test new procedures, all for use in a deadly environment. Space stations will eventually evolve from frontier outposts to homes for a greater diversity of people. But working in space is still risky business, and it demands a highly trained and highly motivated group of people to do the work that has to be done. In the next episode, we'll look at this new breed of worker, the astro worker.
Discovery Houston, it looks like you're heading toward the right place.
I think so. And Dave, I believe we got a tally-ho on it.
Roger that. That sounds pretty good. Old Eagle Eye's up there.
Discovery now within 50 miles from CENTCOM and closing. And the KU band rendezvous radar is activated and has locked on to CENTCOM and is in the passive mode.
And now you're going to close on CENTCOM.
Roger that. We got a bunch of guys looking for it out the top window here.
Discovery has come around into attitude and is now about 331,000 feet from CENTCOM.
And we're cutting the corner on it now, by guys.
That you are.